Okay, welcome everyone. A special welcome to our speaker, Uri Kol, a PhD of Tel Aviv University, who followed with a postdoc at University of Michigan and is today a postdoc in New York at NYU. Uri will tell us about the duality and IR phenomena in Einstein's gravity. Good luck.
Thank you very much, Ofek, and thank you for the opportunity to speak here. Today I want to tell you about a research program we've been pushing in the last couple of years. We've discovered a new type of duality in Einstein's gravity that is similar in many ways to electric-magnetic duality in electrodynamics. And this duality reveals a wide class of infrared phenomena that I'm going to explain. So perhaps it may be slightly different than your usual seminar since it's not strictly speaking about astrophysics, but I will make the case that it's whoever is interested in gravity and especially in infrared phenomena and higher gravity perhaps can find it interesting. So please interrupt me at any point with questions. I will basically talk mostly just on linearized gravity and some knowledge of plain old Maxwell's theory. And I will try to make it as non-technical as possible. So if there are any questions, please. So this is based on a series of works, mostly with these collaborators. And let me start with brief motivation for this study. So the double copy is a known relation between gravity and gauge theory. And I will explain it in more detail about the double copy later, but for now, let me just tell you that it's a well-known relation between these two theories. It provides a concrete map between the two theories. And the question that I want to pose is, given the double copy relation, what would be the gravitational version or the double copy of electric-magnetic duality? And when I say electric-magnetic duality, I mean plain old electromagnetic duality in Maxwell's theory that we all learn in second or first or second year of undergrad in physics. Okay, so this is the motivation for this study.
Can I just ask, what's the origin of the name double copy?
Yes, I will get into it. Essentially, gravity looks in a sense like two copies of gauge theory. And there are different manifestations of this. Today I will show one particular and simple manifestation. It was discovered originally in a study of scattering amplitudes, and then it was expanded. And today there are different results that go under this name. But I will explain more concretely what I mean by that for our needs. So why is it interesting at all? As you all know, there are many open problems and that challenge our understanding of the infrared nature of gravity. Those problems are both theoretical and observational. On the theoretical side, maybe the black hole information paradox, and more observationally, dark matter or dark energy, depends how you classify, but both of them are observational and theoretical, and there are many more open problems. Now, on a different note, electric-magnetic duality has been a key feature behind our understanding of infrared phenomena in quantum field theory for more than a century, essentially since the discovery of Maxwell's theory. And since then, it's been a very important tool in the study of quantum field theory. So what I would like to argue here is that perhaps a similar duality can improve our understanding of gravity. So this is the motivation. And now in order to be able to talk about a duality between charges, let me first review what are the charges that we discuss in gravity. So if we consider, for example, the flat Minkowski spacetime, it is described by this line element. It is well known that this spacetime is invariant under the Poincare group of isometries that includes 4 spacetime translations and Lorentz transformations. The four space-time translations are associated with the conserved charges that are the energy and momentum, as we all know, and similarly, there are Lorentz charges. So this is the starting point. These are the conserved charges that we have in space-time. And the question now is how to describe them, how to give a concrete covariant expression for the charges in the same way that we do in electrodynamics. In electrodynamics, the electric charge, for example, is the flux of the electric field. So how do we give a similar expression in gravity? In order to do that, we need, first of all, to elevate the metric into a dynamical field. So in gravity, we study general relativity is the theory of gravity, and it is a theory of the metric field, which is a tensor of rank 2. And the way to describe the charges is to elevate the metric into a dynamical fields and study conserved charges. And the way we know how to do that is perturbatively. We perturb around flat spacetime and study the fluctuations of the field. So this is the setup. We consider a spacetime that is general in the bulk. In the bulk, there could be any matter distribution. It could be a star, it could be a black hole, it could be anything. And the only thing that we demand is that at large distances, it decays into flat or approaches flat spacetime. So the expansion of the field, the metric field, takes the following form. At leading order, we will have leading order in large distances. We will have the metric of Minkowski, and then there will be a correction that will go like 1 over the radius. And here I parameterize the metric components of this correction in the following way. I call the TT component phi, and the off-diagonal component I will call A. And there are, of course, all the rest of the components, but I avoid writing them just for sake of brevity. They are not independent. They will depend on the components that I already wrote. Phi here is nothing but the Newtonian potential. It goes like the mass aspect. Sometimes it's called the Bondi mass aspect over the radius. And similarly, there are off-diagonal components. Now, to the question of Asaf, we can already see in a way why, okay, you know, I'll say something about the double copy in a minute. So this is the setup. This is the setup.
Can I ask something?
Yes.
So apart from, so once you have the extra terms, so is this like extra terms will be 1 over r square dependence?
Yes. Yes, it's an expansion.
And then the second question is the a's, ax, ay, and az. You treat them as constants, or these are also some functions which are not depending on r, but on something else?
Exactly. They are functions of all the coordinates but r. Exactly, like the mass aspect here in general. For example, for Schwarzschild, this A will be 0, and the Bondi mass aspect will be just a constant, the Schwarzschild mass.
Okay, and what's the logic behind this type of expansion?
The logic is that in gravity, we don't know how to define charges at any distance because we don't have a covariant notion of an area. So we need to consider the charges on very, very large sphere outside the distribution of matter, because otherwise we don't know how to define a covariant notion of area that encloses some flux. Excellent. So this is an old approach. And the first ones to study this problem were Bondi, Van der Burg, Metzner, and Sachs in '62. And they were expecting to define the charges for the Poincaré. They were expecting to find the Poincaré charges. Instead, what they found is a much larger group of isometries. Today is known as the BMS group. It's an acronym after their names that includes, in addition to Lorentz transformations and translations, an infinite amount of super translations. And what are these super translations? This is a group of transformations that leaves the metric that I wrote before invariant. Roughly speaking, they take the following form. And again, I will try to avoid writing all the technical details, But roughly speaking, this transformation, first of all, they depend on a function on the sphere. So for any angle on the sphere, there will be an independent transformation. And the transformation is composed in two parts. One, which includes derivatives acting on the field. And I didn't write everything explicitly to avoid technical details, but this is an example for one of them. It's just a derivative, a time derivative of the fields. And then there is a piece that I will call an homogeneous piece. It doesn't depend on the field. And this is what we call a large diffeomorphism. Because we call it large because it changes the metric components at very large distances. Now, these transformations can be decomposed according to the spherical modes, and it turns out that the 0 and 1 spherical modes, they reproduce the 4 ordinary space-time translations, for which this homogeneous piece vanishes. So for L equals 0 and 1, this homogeneous piece vanishes, and the yellow pieces that I wrote here in yellow, they reduce to the 4 ordinary space-time translations. However, there is an additional tower, infinite tower of higher spherical modes, for which this homogeneous piece doesn't vanish. And those are space-time translations that are angle dependent. And this is the group of transformations that leave the asymptotic metric that I wrote before invariant. So back then, that was a very surprising result. These people, they expected to find the Poincaré group of isometries, but instead they found a much larger group, which is known as the BMS group today.
So again, when you say infinite menu, I'm trying to understand what exactly is being done here. So you're just transforming the field by adding a differential term, which is proportional to 1 over R. And then you get that you can have as many fields like that as you want, essentially?
Yeah, it's not an addition, it's an expansion of the metric field. So this is very general. As long as we, this can be generalized further to include different asymptotics, for example, a cosmological constant. But if we limit our discussion for the sake of the discussion here to the class of spacetimes that approach the flat metric at large distances, this is very general. This is a parameterization of a very general solution.
That's fine, but when you said there is infinite number of isometries, what do you mean by infinite here?
I mean that, first of all, that these isometries depend on a continuous function on the sphere. For every angle, there is a generator of this isometry. And second, what this transformation is doing, it preserves this form of the metric. This is what I mean, and this is what BMS found in the 60s.
Isn't that just a simple manifestation of a symmetry of the problem? That you can basically have a spherical symmetry here, so you can simply rotate in each direction that you want.
It's not spherical symmetry, but yeah, it's larger than just rotations. Rotations are included in the Lorentz.
No, yeah, but okay, it's a symmetry of the Poincaré group.
It's larger than Poincaré, but it's the group of isometries that preserve this form of the metric. Exactly.
And again, can you explain why is it larger than the Poincaré?
Because it includes Poincaré for the L equal to 0 and 1 modes, but in addition, there are more. There are an infinite tower of modes for L greater than 1. So
can you give an example of one of those additional symmetries or transformations?
Yes, I will give an example. Well, this is the transformation law. So here, I didn't write everything explicitly, all the terms explicitly, but you can put, for example, a transformation parameter f with L equal to 2 or L equal to 3. And any of these modes, any of these transformation laws will preserve the form of this metric. This is the claim. And now there are also charges associated with these transformations. So what I want to do next is to tell you how we write the charges for these transformations. And perhaps when I write the charges, it will become more clear. Before I write the charges, I want to introduce the double copy. That will help me introduce the charges. So the statement of the double copy, and this is only one manifestation. There is a series of results that go under this name, but I want to present one manifestation. Imagine we take Maxwell's theory with a scalar and vector potentials phi and a. The claim is that if we map these potentials into the corresponding metric component that I wrote here, that I defined here for a good purpose as phi and a, the claim is that then this metric constructed in this way will solve Einstein's equation. Okay, so the claim again is that if we take these electromagnetic potentials and if they solve Maxwell's equations, then we have a prescription for constructing a metric that will solve Einstein's equation. Okay, this is the claim for the double copy that I want to introduce. And in this sense, it is called double copy because it looks like in the metric there are two copies of the gauge field. So this is the reason for the name. And we can also go ahead and define these E and B fields using these metric components, and those will be the double copy of the electric and magnetic field in Maxwell's theory. Okay, this is the statement. I do not prove it here, but we have proven it, and essentially it was known in the literature.
So essentially what you did, you added up a surface term to the metric.
No, it's not a surface term. It's just an expansion of the metric. It's a very general expansion. The only requirement...
You wrote it in terms of a surface term times some constant in the previous slide, right?
No,
yeah, you have here it is, right? So you have df, or d lambda or df, right?
Yeah, you can call it as, yeah. I mean, this is the transformation of the metric.
Right.
This is the transform, and yeah, it's not a surface term, but you're right. It's a term that doesn't vanish at infinity. It's like a gauge transformation. Usually we demand diffeomorphisms or gauge transformations, they vanish at infinity. And this is a term that affects the metric at infinity, the fields at infinity. And this is why it's called a large diffeomorphism. Yeah.
Okay.
Yeah, that's exactly the story. And this is the claim of the double copy, but let me emphasize that despite this relation, these are two different theories. General relativity or gravity is a theory of space-time transformations, and Maxwell's theory is a theory of gauge transformations. And we see the difference. Space-time transformations involve space-time derivatives acting on the fields, while gauge transformations don't. In this sense, this large piece looks very much like a gauge transformation, but we should not forget that it is part of the entire space-time transformation. So this is the double copy relation and the different transformation laws of the fields in each one of the theory. In this talk, I will be interested, of course, in gravity, and I will use Maxwell's theory mostly as an analogy or to make a connection using the double copy. That will help me introduce some concepts in a very clear way. So most of the talks, when I say phi or a, I will refer to these metric components, unless I refer explicitly to Maxwell's theory. Okay.
Are you only working in the weak field approximation?
Yeah. So it's weak in the sense that it's an expansion. Yes.
Okay, so you're assuming that it's a Minkowskian plus a small perturbation, basically.
Yes, exactly. So, and this is the only way we know how to define charges, as I explained before. But that is correct. It can also be generalized to include cosmological constant, so an anti-de Sitter or de Sitter asymptotic. But it is not needed for the purpose of the results that I will show you. And now using this, I can define the conserved charges in a very natural way. This is not the original way it was discovered, these charges, but using these tools, I can introduce it in a very natural way. So in electrodynamics, we have the electric charge as the flux of the electric field. And using this double copy map, I can now use this definition of this E field and write the conserved charge in gravity. And it turns out that it is the integral over the mass aspect. So that was known for many years, that since the work of BMS. This is the charge, it's the integral over the mass aspect. And we can understand it using the double copy. Now, the monopole mode, the monopole mode of this charge is nothing but the energy, total mass or energy in the system. The L equal to 1 mode of this charge gives the linear momentum. And then there is a tower of charges that correspond to higher harmonics, higher spherical modes.
What do you mean by B? Is that the bound charge, or this is a charge that you basically put at the boundary charge?
This is the charge, the flux of the gravitational field, basically the flux of the Newtonian potential on a very large sphere.
So it's, again, I'm trying to get the physical picture here. You start from a Minkowskian space-time, meaning that there is no mass, and then you're adding a perturbation, which you quantify in a certain way. And you say that this perturbation can originate from some surface charge, which you can put on the boundary of a sphere, essentially. And so the mass that you have here, MB, is this mass that you put in the boundary?
No, the mass is, for example, you can think about it as the Schwarzschild mass. A Schwarzschild mass would be a particular example.
Yeah, but then you're not in the weak field approximation. Then you cannot use this.
No, far away you are. If you are far enough from the black hole, from the Schwarzschild, then you can expand the metric in this way. So Schwarzschild is asymptotically flat. We can expand it at large distances, and the Schwarzschild metric will take this form. So what I imagine is a very general distribution of matter in the bulk. I'm agnostic about the distribution of matter in the bulk. The only thing that I require is that at large distances, it decays to Minkowski, to flat spacetime. And that's very general. Unless we include a cosmological constant, any system will obey this. I don't want to make a strong statement, but it's a very general statement or setup. And now we can consider, given this general setup, we can ask what is the flux of the gravitational field, in particular of the Newtonian potential, on a very large sphere. And the answer is simply this charge. It is called the supertranslation charge, but it is simply a generalization of the concepts of energy and momentum. Okay, any more questions about that?
So in this case, what's higher up in the tower?
Again, what's the question?
What's higher up in the tower of conserved charges?
So these are called the super translation charges. Those are known in the literature as super translation charges, and essentially they describe the distribution of mass, right? It's you smear the mass, you integrate over the mass aspect with some spherical, higher spherical modes.
So mass quadrupole, octupole, etc.
Yeah, exactly. And now I'm getting to the main question. So given this super translation charge, and I hope that I managed to convince you that it is related not just by analogy, but also by the double copy into the electric charge, then we can ask the question, what about the magnetic charge? In electrodynamics, we have a magnetic charge. And what is the double copy of this charge? And this is the new charge that we found.
When you say magnetic charge in electrodynamics, you mean the identical zero?
It's identical. Okay, I will get to review the situation in electrodynamics soon, but it doesn't necessarily have to be zero. We didn't find in experiments magnetic monopoles, but in Maxwell's theory there could be magnetic monopoles, and there is very old and long literature about it. So there could be magnetic monopoles in theory. Very good. Yeah, very good question. So, so that's the question that essentially I'm posing and that we answered. What is the double copy, or what is the gravitational version of the magnetic charge? And we named it dual supertranslations in reference to electric magnetic duality. So, sorry, what is this charge? Well, at the level of writing the expression, it is given exactly by the expression for the magnetic charge, except that here A now is defined with the off-diagonal components of the metric instead of the vector field in electrodynamics. And it can be shown that we have shown that it is a conserved charge indeed. I will not show the derivation, but using the tools that I have introduced, we can write it immediately. And the main question that we asked right after discovering this charge is, what is the transformation law, or what are the transformation laws that this charge induces on the field, on the metric? And what we found is that this transformation law receives contribution only from a piece that looks like the homogeneous piece. There are no derivative terms, like for super translations. In particular, it means that for the lowest harmonic modes, 0 and 1, there are no corresponding transformations. Or in other words, there are no dual transformations for the 4 ordinary translations, only for the tower of super translations. So this is what we call now dual super translation, dual super translations. And it looks very much like a gauge symmetry rather than a space-time transformation. Now, what I want to argue is that it doesn't just look like a gauge symmetry, it is a gauge symmetry in the following sense. In Maxwell's theory, we can write a local magnetic charge density in Maxwell's equations. It hasn't been found in experiments, but the theory does not prohibit writing such a term. We can definitely, and people extensively studied this theory and generalization of this theory by putting a magnetic charge density on the right-hand side of the magnetic Gauss law. That certainly can be done theoretically, and that will produce a magnetic field. Now, it turns out that in gravity, we cannot do that. We have shown that what I call the B field obeys a Bianchi identity, which is proportional to the Bianchi identity for the geometric, for the Riemann tensor. And therefore, in general relativity, it is 0 by definition of what is the theory of general relativity. In general relativity, this is satisfied, and therefore we cannot introduce something that looks like a gravitational magnetic source. The stress tensor looks like the electric source in Maxwell's theory, but there is nothing which is equivalent to the magnetic source, and therefore there is no way to locally source the charge. And in this sense, the dual supertranslation is a gauge redundancy because there is no way to observe it using local measurements. There is no way that we can couple local charge density to the field. So it doesn't produce the action of space-time transformations, and there is no way to observe it locally. And that led us to the conclusion that dual supertranslation is a gauge symmetry of the metric. And this is, in a sense, a very surprising and shocking result. It means that general relativity is not only a theory of diffeomorphisms, like we usually think about it, but the metric also contains an internal redundant symmetry of the field, in the same way that Maxwell's theory has redundant symmetry or redundancy in the description. So this is perhaps one of the main results, or the main results that led to many more conclusions. And if there are any questions, I'll be happy to take them.
If you look at the part that you dotted out, the spatial tensorial part of the metric.
Yes.
What happens to that under these transformations?
Yeah, it's a very good question. They transform in a certain way. I didn't write it explicitly to avoid all the technical details, but they are not independent. At this order, we can choose a system of coordinates in which these other terms, they are functions of these terms. We have freedom to choose a system of coordinates, and using this freedom, we can choose them to be not independent of these components. And using these transformations laws that I also didn't write explicitly, but they are known, you can also deduce what are the transformation laws of all the components. So it's known. It's not. Yeah, I just avoided writing all the technical details. Yeah,
okay,
very good.
But then, for example, if I take a vacuum with gravitational waves, it wouldn't work, right? Because then you only have those tensorial parts. You have nothing. Phi is basically 0. And they're not independent. I mean, A and phi can be 0, but you'll still have something.
So I'm not saying that they are not there. They are there, and you're right. For gravitational waves, phi perhaps will be 0, and then I will be forced to write them down explicitly. But I just try not to write all the details explicitly. But they are there, definitely. Yeah, I'm not claiming that they are not important for the story. I just try to present the story in the simplest possible way. And I can show you maybe after the seminar what are the transformation laws exactly of all the components. Does it answer the question? Or? Yeah, all the metric components transform under this. I just didn't write everything explicitly because the explicit expressions are a bit longer. I didn't want to. Maybe some of the people in the audience are not very familiar in day-to-day life with this kind of expressions.
Is your conclusion relying upon the way you decide to decompose the metric in the first place?
No, it doesn't depend on it. It's true that you can write or describe the metric in different ways. In particular, you can choose different systems of coordinates. I use the standard, well, in this field, it is standard to consider something like that. It is called the Bondi metric, but definitely you can use different system of coordinates to describe it. But the conclusion does not depend on it, right? The flux of the field is the flux of the field. Yeah, very good. So let me mention one important property of the new charge, and then I will stop for summary and questions. And exactly as Ofer said, this charge is essentially 0. It's essentially 0 if the metric is regular. If A, which is the off-diagonal metric component, is regular, it is 0 because of the Stokes theorem. The only way for it to be non-zero is if this A is not regular. If it is not regular, if there are some singularities, then by Stokes theorem, this surface integral will transform into a contour integral around the singularity. And this is also well known in electrodynamics. In electrodynamics, this singularity is called the Dirac string, and I will very soon explain in more detail. And it turns out that there is something similar in gravity. The implication of this is that this charge is invariant under any smooth, regular deformation of the metric. And this is the definition of a topological invariant. It's a quantity that is invariant under any deformation of the field. And there is a similar property in Maxwell's theorem. The magnetic charge is invariant under any deformation of the gauge field, which is regular, of course. So it has this topological feature, and in a similar way to electrodynamics, the dual supertranslation charge or the gravitational magnetic charge, it classifies the space-time geometry into distinct topological sectors in a very similar way to the magnetic charge in electrodynamics. Maybe not everyone are familiar with the concept of topology, so I will not go into much detail, but that's what I want to say, that this is the definition of topological invariant, a quantity that is invariant under any deformation of the field, and this charge obeys it. And of course, it has further implications that I will be happy to discuss further maybe after the talk. Let me stop for a short summary of what we found so far, and then I will show some examples and applications. So we've shown that the double copy relates the electric charge in electrodynamics into what I call the supertranslation charge in gravity, which is essentially the integral over the mass aspect with different weights. Okay, this charge is well known and well studied in the literature. And the question that we ask is, what is the double copy of the magnetic field? And we found a new dual supertranslation charge. So you can think about it as a dual mass if you want. And indeed, this is a charge that looks like the dual mass. It generates gauge transformations as opposed to diffeomorphisms, and it is a topological invariant. The electric charge, for example, is not a topological invariant. It changes when we deform the field. So this is what we found, and now I will show some examples and applications, unless there are some questions that I'm happy to take.
Like we have this in electromagnetic theory, the magnetic fields are generated by the changing electric field or the moving charges. Do you say that the similar picture takes place in gravity also, when the source moves or the Schwarzschild mass moves, it produces the similar magnetic charges, or what is the origin of the magnetic fields in?
Yes, so in electrodynamics, moving electric charge will generate higher harmonic modes of the magnetic field, right? A dipole, a quadrupole. But in order to have a monopole, a magnetic field from monopole, you really need a magnetic monopole. You cannot produce a monopole magnetic field with moving electric charges. Okay, so this is most what is the story about. And of course, there are also higher harmonics, and I'm going to mention it. So that's a very good question, and it brings me to, to review the theory of, very briefly, the theory of magnetic monopoles in electrodynamics. So the magnetic monopole is a genuine charge, right? It, again, related to what you said, it cannot be produced by moving electric charges. And also, it cannot be described by a regular gauge field, for the reason that we showed before. If the gauge field is regular, then the magnetic charge will be zero. And this question was addressed by Dirac back in 1931. Dirac found that in order to describe a magnetic charge, you need to introduce a singular gauge field. And this is the gauge field that I wrote here. In this form, it is known as the Dirac-Schwinger potential. It is singular along the z-axis, theta equals 0 and theta equals pi. And it produces the magnetic field of a monopole. So in order to have a magnetic monopole, we must allow for the gauge field to be singular. However, as already Rak argued in his original paper, the singularity is not physical. It's only an artifact. And one way to see this is, there are also semi-infinite Dirac strings. So using gauge transformations, we can move the string around. And the potentials that describe the semi-infinite strings are given by those expressions. Correspondingly, they are singular only on half of the axis. And one way to see why this Dirac string is unobservable or unphysical is using what is known as the Wu-Yang construction of a magnetic monopole from 1976. Wu and Yang constructed a monopole solution without singularities in the following way. They took the northern hemisphere of a string pointing in the negative direction and glued it together with the southern hemisphere of a string pointing in the positive direction. In such a way, they were able to write a solution without a solution for a magnetic monopole without any string singularities. The only possible problem that can appear here is some discontinuities around the equator, right? But what they showed is that on the equator or around the equator, the two descriptions are equivalent up to a gauge transformation that I wrote here. So if the two descriptions are equivalent up to a gauge transformation, it means that they are physically equivalent. And this is the Wu-Yang construction. These two patches, they both generate the same magnetic field. And this is one way to explain why the Dirac string is unphysical. It can be eliminated. Okay, so this is the story, in brief summary of the story of magnetic monopoles in electrodynamics.
So again, this means that B is a perfectly fine magnetic field, and it's well defined everywhere, but there's no regular A.
Exactly. There is a tension between having a magnetic charge and having the field described in terms of a regular potential. Exactly for the reason that you also mentioned before. And this is a well-known story. There is a very rich literature about magnetic monopoles, also in more complicated field theories. And yeah, this is a well-known story. And now, let me move on to gravity. What is the situation in gravity? Do we have an example of a space-time that has a non-zero dual super-translation charge? And the answer is yes. This solution is known in the literature as Taubnat, after these people that discovered it. I wrote it in the form of the metric explicitly, but it's not essential for people that are not familiar with these notations. The important thing is that this solution is described by two parameters: the mass parameter, which is essentially the same as the Schwarzschild mass, and a parameter that is known as the NAT parameter. NAT, again, named after these people, Newman, Unti, Tamburino, that discovered it. And this metric is known to exhibit a conical singularity known as the Meissner string. In this form of the metric, the Meissner string appears along the entire z-axis. And then one can go ahead and compute the dual supertranslation charge, and it is non-zero. It is proportional to the NAT parameter. So the NAT parameter is essentially, or the dual supertranslation charge is a generalization of what is known in the literature as the NAT parameter. And one can expand this metric at large distances. And what happens is that the metric that I wrote before takes the following form. This is essentially, again, the Newtonian potential that you are all familiar with from the Schwarzschild case. But in addition, there are off-diagonal terms that take exactly the form of the Dirac-Schwinger potential in electrodynamics. So this is the analog of magnetic monopole in gravity, or maybe I should say a magnetic diode that includes both electric and magnetic type of charges. And this example shows also the connection between the topology, the non-trivial topology, which is due to the singularity, the non-vanishing charge, and the magnetic mode.
What is conical about this string or singularity?
Yeah, so you see here in the metric, we have the factor d omega squared. This is the metric of a sphere, right?
Mm-hmm.
But in addition, we have a contribution from here that will go like d phi squared that will deform the sphere. Will deform the sphere and will create what is known as a conical singularity. Essentially, in order, because of this term, the metric, the asymptotic metric is not a metric of a sphere. Or in other ways, the angle phi, this metric is not invariant under rotation in 2 pi. There is some cone angle, and the metric is invariant under rotations that are different than 2 pi. So this is called conical singularity. And this has been known for many years, and the space-time is known for many years, since 63, essentially, 1963. So this is not new. What is new is and before I say what is new, let me also mention that there are also solutions corresponding to semi-infinite Meissner strings, similar to the semi-infinite Dirac strings. And an open, long-standing problem in the literature was how to eliminate the Meissner string. So how to write a solution without any singularities. Because if the singularity is real, then it means that it is physical, and we don't like physical singularities. We would like to have a monopole solution without singularities. So this has been a long-standing problem, and now what I will show is that we have the tools to address it. Now we can construct a gravitational Wu-Yang monopole by gluing together 2 patches of semi-infinite Meissner strings. We took the northern hemisphere from a Meissner string in the negative direction and glued it together with the southern hemisphere of string pointing in the opposite direction. This solution, constructed using the metric on 2 patches, is regular, but we have to make sure that it is also continuous along the equator. And we show that this is indeed the case because of dual supertranslation gauge transformation. We show that on the equator, the 2 descriptions are related to each other by a gauge transformation, which, as I argued before, is unphysical, and therefore the 2 descriptions are equivalent, and the solution is continuous and differentiable. In particular, the dual supertranslation charge of this monopole solution receives equal contributions from both patches, such that at the end it is equal to the charge of the original Meissner string solution. Okay, so for this, I want to emphasize that for this construction, it is essential to know about this gauge transformation, because before we knew about these gauge transformations, we couldn't have done that. We couldn't have identified the 2 patches on the equator. So that's the new ingredient, and that allowed us to write a regular gravitational magnetic monopole solution.
So does this then break the Bianchi identity?
That's a very good question that is still work in progress. It doesn't. So this metric is locally flat. Where did I go? This metric is locally flat, which means that it doesn't violate the Bianchi identity anywhere except the string. So we accept to have a violation of the Bianchi identity, perhaps around the string, but this is something that we still looking at. But it's a very good question. What we found is that we can, let's see, let's go back to the Bianchi identity. This Bianchi identity can be violated, but in order to do that, we need to consider generalizations of GR, because in GR, this Bianchi identity is 0 by definition. And such a generalization is known as the Einstein-Cartan theory. It's a theory with something that is called torsion. I'm not sure if you're familiar, but it's a theory with a property that is called torsion. And in this theory, this Bianchi identity is proportional to the torsion and is violated. So this violation will require the introduction of torsion. Very good, yeah. So now, in gravity, there is a potential pathology that could appear that is not there in electrodynamics. We want to avoid the appearance of closed timelike curves. This also has been, without getting into details, it's been longish, an issue that was studied in the literature, and there is a rich literature about that. And what we found is that our monopole solution is devoid of closed timelike curves in this region of parameters, when the mass over the NAT parameter is smaller or equal to this number that we found, and this is our prediction for the monopole. Now, perhaps some of you are familiar with Kerr metric, a rotating black hole, and in the Kerr metric, we also have a similar bound on the ratio of the mass to the spin or angular momentum parameter. And so this is not the same bound, it's a different bound, but they both seem to follow from the same principle, which is in essence some form of cosmic censorship. So it's similar, it's a new bound, a new prediction, I would say. And here is where I want to turn into people with more background in astrophysics and ask the question whether we can observe this gravitational monopole in the sky. Of course, I don't have an answer for that. I'm trying to reach out to astrophysicists and see if this can be done. One way this could potentially be observed is the following. Imagining that this gravitational monopole exists, we can try to look at the motion of stars around it, like that, and try to observe a force that is that looks like a magnetic monopole. Now, in order to do that, we need to consider the motion of stars or any other quantities around this monopole. This is done using the geodesic equation, and what we've shown is that the geodesic equation takes this form. Takes a form that is very similar to the Lorentz force in electrodynamics. There is a force that takes the form of an electric field, and there is a force that looks like the magnetic force, where E and B are defined again using the metric components. Here M0 is the mass of some probe particle, or let's say a probe star moving around potentially such an object, and gamma is the Lorentz factor. So it takes a form very similar to the Lorentz force, except that the coefficients here are slightly different. The coefficients in front of the forces are slightly different. They depend on the Lorentz factor. And in the limit of small velocities, this is known as the Newtonian, the post-Newtonian approximation. In this limit, this formula was essentially known. We generalized it for finite velocities. So here gamma is finite, doesn't have to be the velocity of the particle of the star doesn't have to be particularly small. But in the limit of small velocities, it was known. So my suggestion, and I've been trying to reach out to astrophysicists, is to try to measure it. We can try to look at motion of stars around, well, maybe black holes or maybe other objects, and try to measure gravitational magnetic monopole, which can also be differentiated from regular magnetic monopole in electrodynamics. In principle, a black hole could also have a magnetic charge in the usual sense, but we can differentiate these two forces because the coefficients here are different. So this is a potential way to discover this, and I'll be happy to talk more with people if there is any interest. Let me try to approach the end of this talk by saying that first of all, we've extended this duality into the subleading orders. So the monopole charges in gravity describe the supertranslation and dual supertranslation charges. And the dipole gravitational charges describe the generators of boost and rotations. So this describe the Lorentz charges. And we've shown that in a similar way, this duality, electromagnetic type of duality, mixes the generators of boost and rotations in the same way that it mixes supertranslations with dual supertranslations, or the mass with the dual mass. And this is what we call the extended BMS group. And then we could also consider a class of solutions that are charged under all these charges that I describe in this table. So if we start with the Coulomb electric charge, for example, we can, using a duality transformation in electrodynamics, we can transform it into a dione. A dione is an object that has both electric and magnetic field charges. And then we can also spin it. And it turns out that we can now do something similar in gravity. We now have the tools to discuss duality in gravity. And this duality maps the Schwarzschild solution into the Taub-Nat solution. And then we can also spin. We can also add spin to the system. By doing that, we transform Schwarzschild into a Kerr rotating black hole. And we can now discuss the action of these two operations simultaneously. And that leads to a solution known in the literature as Kerr-Taub-Nat. And each one of these operations, spin and duality, and each one of these theories can be related to each other by the double copy structure that I described before, except that for this class of solution, the double copy is an exact relation. What I showed below, before is an asymptotic form of the double copy, which is general and doesn't depend on a particular solution. But what I claim here is that for this particular class of solutions, the double copy is an exact statement to all orders. I don't show it, but this has been shown. So we have here a class of solutions in different theories that are related to each other by three operations: duality, spin, and the double copy. In general, these operations can be complicated, but there are certain observables which transform on which this operation acts very simply. And such an observable is the 3-point amplitude. I will not go into detail because I know that it's a seminar in astrophysics and perhaps people are less familiar with concepts from field theory, but just to mention that there is a 3-point amplitude for scattering of particles. And it turns out that this quantity transforms in a very simple way under these three operations. First of all, the duality acts on this observable as phase shift. Spin acts as a real exponentiation. And the most interesting thing is that the double copy is simply a squaring of this amplitude. So if we want to compute the 3-point amplitude of scattering of a probe particle from a background field, whether it is in Maxwell's theory or in gravity, all we have to do is to square it. And this is another manifestation of the double copy. This is another reason to understand the name double, because it's squared. So starting from the scattering of a Coulomb charge, of scattering of a probe particle from a Coulomb charge, we now have a web of amplitudes, and we can easily compute scattering of a probe particle from a fairly exotic object like this Kerr tab nut metric, which some people may consider as exotic, since it's not an object that most people, unless they are excluding experts in the field, will consider. And indeed, we were able to compute the scattering of a probe particle from these background fields in a straightforward way using these results. I can tell more for people that are interested. Let me summarize the main results. We have found a new gravitational magnetic type of charge, which gives rise in turn to a new gauge symmetry, redundant symmetry of general relativity, which is not different morphisms. That allowed us to construct a gravitational magnetic monopole solution and address a very old problem or puzzle in the literature of how to interpret this Meissner string in a physical way. And it gives rise to a duality, a new type of gravitational duality, which is similar, analogous to electric magnetic duality in Maxwell's theory. And in fact, it's not just an analogy. As I showed you, there is a very concrete map that is called the double copy that relates the two things. So let me end with some future directions. And here I would like to emphasize the observational signatures of this dual mode. So I already mentioned one possible direction of trying to observe these monopoles using the motion of stars around it. And we also currently, it's a work in progress, we study quantum mechanical scattering of the monopole, and hopefully that will appear soon and I can tell you more about that. And right after we finish with that, the plan is to study something, or to study the signature of these dual modes on gravitational waves. And I know that there are experts in the group in Bar Ilan on gravitational waves, so perhaps it would be interesting to discuss and maybe collaborate on this issue. But definitely we are planning very soon to start studying the signature of these dual modes on gravitational waves. Perhaps the most immediate thing to do is to consider a binary system of two monopoles rotating around each other and see what is the gravitational waves that they emit in similar way to the way it's done for Schwarzschild black hole. And now we have all the tools to do that. So we are going to address this question very soon. And then there are a few more theoretical questions, I would say. Let me finish with the thought, leaving you with the thought that perhaps the gravitational monopole has already been observed. Perhaps it can explain phenomena such as dark matter or dark energy. I don't have something concrete to say, but definitely we are looking to try to explain dark matter, or at least some of the observations that fall under the name of dark matter, using these new results. For example, many people that work on dark matter try to explain these observations using a new type of force. So what we found is perhaps a new type of magnetic type of monopole force that could potentially address some of these problems. And really, let me finish here in this slide by saying that in field theory, electromagnetic duality and gauge symmetry have been fundamental principles behind our understanding of infrared phenomena in quantum field theory for a very long time. So I want to suggest here that perhaps the gravitational duality that we found and the new gauge symmetry provides a promising place to look for solutions to all these problems. So I will end here. Thank you.
Your formalism is based on weak field approximation. At the same time, you suggest that the effect of monopoles can be observed in orbits where two stars are orbiting around each other. So isn't it the weak field limit may not work there?
Maybe it's possible, but you can also think about a system, a star that is moving very far from the object, in which the weak field approximation is valid. So it's certainly possible that such a system could exist. Yeah. But that's a very good point. Yeah, this analysis is in the weak field approximation. That's true.
So two similar electric charges repel each other, two similar masses attract each other, but two similar magnetic currents attract rather than repel, while two mass currents repel rather than attract. How would these monopoles behave? Would they be attractive or repulsive? Could you even form a closed system between two monopoles?
Yeah, it's a good question. What I can tell you is that at least for objects that move according to the geodesic equation, that will be the force that will act on them. And we haven't studied a system of two gravitational monopoles. So it's a very good question. And this is part of what we plan to do very soon. Study a binary system. Yeah.
On the astrophysical side, it might even be simpler before looking at a system of two such monopoles. Looking at one monopole with either a star around it, like a black hole that also has a magnetic monopole, or even a black hole with a large magnetic monopole with light bending around it. And for that, we have an image you might want to look into.
Yeah, definitely. And I'm more than happy to discuss it further. You are the experts on gravitational waves, and yeah.
That's not even waves. That's the Event Horizon Telescope is completely, in some sense, classical.
Yeah, so I'm not sure how to. Yeah, if you have an idea how to try and observe this monopole there, I'm happy to talk. The idea that I had in mind is to study binary system and the gravitational waves that they emit, and we have the tools to do that. Yes, I'm more than happy to hear other ideas. This is part of the reason that I'm trying to reach out to astrophysicists.
On the gravitational wave side, you'd have multiple obstacles. The first one, of course, is if you have to assume torsion gravity, you'll have many more degrees of freedom.
Yes.
And many more theoretical modes in which you can emit. I'm not even sure you'll be able to maintain the leading order quadruple formula in that case. But it might be simpler to look at a non-dynamical system, like stationary orbits, like the black hole center of our galaxy with stars orbiting around it, or the M87 galaxy with photon trajectories and images of the light around it. I don't know how either of these will behave in torsional gravity.
Yes, that's very good questions, and I don't have complete answers, but what I can tell you is that the understanding of how these objects are sourced is not necessarily important for these questions, and for the following reason. The same way that for Schwarzschild black hole, so the Schwarzschild source is a delta function, right, at the origin. But except at the origin, everywhere else, the Bianchi, let's say the electric Gauss law is not violated. So for the sake of computations outside the origin, we don't care about how the source looks like. The metric is essentially Ricci flat everywhere except the origin. So it's possible that in a similar way, if we want to compute certain observables away from the source, the magnetic source, we will not have to discuss torsion. Did I make myself clear?
Yes, you only want to violate Einstein's gravity on a very locally.
Exactly. Oh, yeah, I wouldn't say locally because this is non-local, but in specific regions of space-time. And the observation that we want to make does not necessarily involve these areas of space-time. Exactly. So, but I mean, the point that you raise is good. It's not something that we studied, so it has to be addressed. But my guess is that these gravitational waves will not necessarily involve torsion.
So this Kerr-Taub-Knot solution, does it have a metric and the magnetic field one can look at?
Yes, definitely. And we recently wrote a paper about that. It's a generalization of this metric. This is the Taub-Knot metric, and if you add angular momentum or spin, that will be the Kerr-Taub-Knot. And yeah, and the form of the metric is well known. I just avoided writing it here, but definitely, and I'm happy to discuss it further and show you the explicit expressions.
And there's no electric field, just a monopole magnetic field.
So it depends. I mean, the Taub-Knot and the Kerr-Taub-Knot are the analogs of a dione. So there is an electric field, which is proportional, electric type of field, let's say, because it's not an electric field, but it is proportional to the mass. So there is, but to simplify things, we can turn it off. We can set the mass aspect to 0. Yes.
Well, you still have the limit of m to n, right? The 27/5 or whatever it was.
So for the monopole, yes, but m equal to 0 does not violate this bound. So I believe that.
Oh wait, I now see that this limit is actually the opposite of the Kerr limit.
It's opposite to the Kerr limit. Exactly, that's true. It's opposite. It's not the same limit, but both seem to follow from the same principle. For Kerr, we try to avoid naked singularities, and here we try to avoid closed time-like curves. And we know in the literature that there is a relation between closed time-like curves and singularities. Essentially, you see what is the reason. The reason is that we want to avoid this Meissner singularity. So
yes, but if I take any Kerr black hole and a Schwarzschild black hole, a simple one, and I merge them together, I get a Kerr black hole with a lower spin parameter, so it's further away from the bound. But in your case, if I take a regular or something, and I merge it with a black hole with a magnetic monopole, now I'm at a risk of violating the bound because I increase the wrong side, right?
If you try to merge two of these gravitational monopoles, I mean, perhaps
okay.
yeah.
I'll put it another way. Now there's this gap, right? I can have n equals 0 black holes, and I can have n greater than some factor m black holes, but I can't have anything in between. So now the allowed region now is not continuous.
Yes, that's true, and this bound in general is not continuous. You cannot take the limit that n goes to 0 continuously because of the topological property. The topology is not continuous. Once you introduce the charge, no matter how small it is, the topology will be non-trivial, and this is why this bound is not continuous. And I agree with you in a sense. Perhaps in a binary system, one has to study it more carefully. But once you introduce the charge, even if it's only one of the magnetic fields of the black holes, let's say, the topology of the space-time is non-trivial already. So that's definitely true that it's not continuous, and we have to pay special attention when we study binary system, definitely. So I want to emphasize that despite the fact that these matrices, term naught, they have been known for many years, people usually consider them pathological for the reason that I mentioned, because of this singularity. So they did not receive, maybe I should say, the attention that they could have deserved because of this reason. But now we have the tools to consider them more seriously, because we've shown how to interpret them physically. So many of these questions that you've asked, in principle, could have been asked in the past, but for this reason, they were not addressed.
There's a question in the chat, if you can see it.
Let me see. For some reason, I can't see the chat because I'm sharing. I'm sharing the screen.
Okay, I'll read it then.
Yeah.
Can you explain again why is the gravitomagnetic new gauge symmetry not a general diffeomorphism?
I can explain it, but I did not provide the full details. The devil is in the details, and I try to avoid them. But essentially, once you introduce this charge, you can compute its action on the phase space, on the fields in the phase space. And this is what we did. And the result is that there are no derivative terms. Now, actually, this can be understood in the following way. For the supertranslation charge, we can decompose the supertranslation charge into two pieces, one that we call out piece and one that we call soft piece. The soft piece receives contributions from 0 energy modes of the graviton only, and the out piece is essentially the integral over the stress tensor, namely non-zero energy modes. This out piece is exactly the piece that generates the derivative terms. The stress tensor generates the derivative terms, and the soft piece generates the homogeneous term. And what happens is that for the dual charge, it turns out that there is only a contribution from soft modes. There is no out mode contributions, and exactly for this reason, there is no local out charge density for this field, for this charge. So that corresponds only to the action of soft zero energy graviton modes, and it generates only the homogeneous term. So there are no derivative terms, and this is exactly why it's not a diffeomorphism. Diffeomorphisms are generated by derivative terms acting on the fields in the phase space. Yeah, very good question. I should have emphasized it in the talk, but this is essentially the reason. And I hope that it's more clear now.
Any more questions? Going once. Going twice. Okay, let's thank our speaker again.
Thank you very much, and yeah, I hope that
Thank you very much.
if people are interested, we can discuss some aspects. Especially, I'm interested in